So there we go. What we're going to, again, my apologies for the delay. What we're going to talk about a little bit today, we're just going to go through this agenda very quickly. We're going to look at Owens Corning's industrial mineral product offerings and the fantastic products we have to offer there. I have a brief overview of ASTM standards and test methods, and I tend to think of these as kind of the rules that we play by when we're specifying materials and products for use in your applications. We're going to have a thermal performance overview. Some of you more experienced folks out there, this is going to be maybe more of a review, but we'll go over it quickly, so hopefully it won't be too painful for you. We're also going to have a quick fire performance overview to kind of show some of the testing that's involved with these materials and make sure that they meet the requirements for the challenging environment that industrial insulation applications see. And we're also going to talk about corrosion under insulation, do a brief explanation there, as well as some strategies to help prevent corrosion under insulation with your particular jobs. And then we're going to follow up with an acoustics overview about some exciting new results that we've had with our products recently and how you can use that to quiet down your facility. To start off with, though, just so you know who's presenting, this is Owens Corning. We're a $7.1 billion company employing 20,000 employees in 33 countries. We have 3 businesses that we participate in, primarily residential roofing, insulation for a wide variety of applications ranging from -450 degrees Fahrenheit up to 1250 degrees Fahrenheit, as well as composites. So to start off with, the portfolio that we have to offer is mineral wool, and mineral wool as a material it works really well in high temperature environments. Even though we have a maximum use temperature of our products of up to 1200 degrees Fahrenheit, the fibers themselves don't start to melt unless the temperature is in excess of 2000 degrees. So that means it's not going to melt or shrink or crumble or do any kind of catastrophic failures in the event of a challenging event. The material is also tough, which means you can handle it without it breaking, crumbling, or cracking, but it's also easy to handle and to fabricate. And it also has a lighter weight. Generally, the products that are used in industrial applications are going to have an 8 pound per cubic foot density, which when you look at the variety of materials that are used in those applications, it's about half the weight. And we'll talk about that a little bit later. And then finally, we also offer water resistant mineral wool products for use in applications that do require the shedding of water to help reduce the potential for CUI. Now, one of the, to kind of work from left to right, we have our Thermofiber Pro section, water resistant product. These come in a 4-foot section for productivity, so you can install it faster. Not only that, you have fewer cracks and butt joints, so fewer opportunities for moisture to get into the system. Next, we have our Thermofiber Industrial Board. We provide this in a range of, a wide range of densities, ranging from 4 to 15 pounds per cubic foot. Depending on what your application is going to need, and we make a material that's going to provide the performance that you need. And then finally, we have our Thermofiber Industrial Wrap. It's available in 3-foot widths. These products are typically used for larger tanks and vessels, and it offers the flexibility to be able to go around those curved surfaces, but also provides the equivalent thermal performance that you would have in a board or a pipe product. So enough of the commercials, on with the presentation. To start off with, I think whenever you're being asked by an insulation company to use insulation, I think the first question that comes to mind is, why do we care? Fundamentally, what we're trying to do is reduce the rate that heat travels into or out of a system. And for industrial processes, we have these 6 reasons. We want to reduce energy costs, because whenever we have to heat something, we have to put energy into something, and energy costs money. It also reduces the size of the equipment we need to heat things, so we save some money there. It improves process control, so if we're trying to maintain certain temperatures for a certain process, those are much easier to maintain with insulation. Also, if we're not using as much fuel, we're not burning as much gas, coal, or any other potential fuel source, which is also going to reduce the emissions that are coming out of that. Now, the other part of this, and safety is towards the end, but it can't be overemphasized. You want to make sure that you're covering hot surfaces so that people can't come into contact with them and burn themselves. So insulation helps provide a cooler surface to prevent those burns from happening. And then finally, for the accountants in the group, there's a quick return on investment for insulation. Typically at the elevated temperatures that you see in industrial processes, you will see a return on investment usually within 2 to 3 years. It's a very quick return. So to start off with, let's talk about our rules, ASTM requirements. Now, why do we need ASTM in the first place? It seems like we're trying to do our job unencumbered, but actually using ASTM helps to simplify things and provide some shorthand so that we can specify materials and get them done faster, or get our jobs done faster. And as an example, it's simplicity. Because we don't have to gather test methods for every single material and trying to collect them together and then present it to somebody as being adequate for what we're using it for, it's much easier to say that we meet a standard specification and it has all the accompanying test methods associated with it to make it useful. It also provides a minimum acceptable level of performance. So this kind of takes it out of whoever's specifying it to determine whether it's appropriate or not, or whether it passes that criteria. But now if you have something that passes all the requirements for a standard specification, it's much easier to say that it passes that rather than a dozen test methods. The nice thing about this, I think, is that it's consensus-based. It's not a group of producers getting together and trying to force fit what the market wants. It also solicits that input from users and consumers to try and develop standards that are both relevant and useful to the marketplace. And on the other side of that, the manufacturer can develop products based on those requirements to make sure that they meet the requirements of the market. I'd also like to emphasize that manufacturers are limited to only having 50% of the voting that goes along with developing a standard or a test method, so that you don't have an overly represented manufacturing presence in those organizations. Then finally, ASTM is recognized internationally. It's referenced in the International Standards Organization, or ISO, and Canada also uses that as a reference in a lot of cases. So if they don't actually use the ASTM test methods, they'll a lot of times reference them. So where do we start? As I mentioned earlier, there's standard specifications and test methods, at least for what we're talking about today. And so we're going to take a standard specification, and as an example, we have ASTM C552, which is a cellular glass thermal insulation. And under that specification, you might have a dozen test methods, and you see on the right-hand side of the screen, we have things like, we have some thermal testing, we have fire testing, we have measurements of how it's going to perform in the presence of moisture. And a lot of these tests are going to give an answer. They're not going to give a pass-fail. Maybe the only one that's on here that's a pass-fail is some of the corrosion tests and combustibility. And those, it's either you either pass the test or you don't. But a lot of these other ones are a little more arbitrary, and it's up to that standard specification to determine whether it's appropriate for a certain test result in a given application. And so as we go down the left-hand side, we see we have that for mineral wool, we have it for blankets, pipe, we have it for calcium silicate, we have it for perlite. So even though they might be different materials, they still have a lot of similar test methods. And we see that on this slide. If you look along the top, we have 4 different material types. We have mineral wool, cellular glass, calcium, perlite. And because it's a thermal insulation, it's going to have a thermal test associated with it. That just goes along with the title. It's also going to have a maximum temperature, which also is a hint of where we're going to use this product. And if it's an industrial product, it's typically limited to around 1200 degrees Fahrenheit. We're going to have things like linear shrinkage. How much does it shrink as it expands and contracts? If you look at the center part where it's the heavy black line is around it, you see we have 3 different moisture tests, and these are 3 different materials or 4 different materials, and they respond differently. Mineral wool is a fibrous product, so maybe water content isn't appropriate, but maybe how it reacts to water vapor is. Cellular glass doesn't allow any water to pass through it. Or you look at calcium silicate or perlite, because they're molded products that use water or some kind of liquid, they're going to have some moisture entrained in that. So we have 3 different tests to kind of measure what's appropriate for those applications. And As you go down, shock content is just specific to mineral wool products, but wouldn't be appropriate for the other ones. So you can see why we have differentiation between these. And then we also have flame spread and smoke development with all of these because we want to know how they were going to react to fire. And we'll talk about that a little bit later in the presentation. Then finally, we have combustibility, which is going to be listed in the calcium silicate and perlite products, but not necessarily mineral wool and cellular glass, although you will see on data sheets for individual products, they will show that they pass those tests. It is an important criteria. So that's kind of as far as the specification side of this. And maybe one other nuance to this is a lot of times we're specifying a material. We're not specifying necessarily its configuration, but in the case of the pipe specification for mineral wool pipe, you can have something that's formed into a tube like a molded mandrel round product or a cut pipe, something like that. And that'll be a type 1, 2, or 4, depending on the maximum use temperature and some other characteristics. Or you might have a type 3 V groove, which is actually made from a board product. So sometimes you'll see some of these used interchangeably. And the important thing to remember is that they all have to meet usually the same requirements in that standard specification. So you just want to be aware of that if you're switching products or have to do substitutions. So moving on to thermal performance, I'm just going to do a quick overview. And again, just wanted to reiterate, why do we care? We talk about thermal insulation. We have the 6 reasons that we talked about, but just to remind you, it all kind of starts with how it performs thermally for the 6 reasons that we already talked about. So what we do, we're going to start with how we measure and then how we use this information. So how we actually measure it is we put an insulation sample into a device that you see over here on the right-hand side of the slide. We'll take an insulation sample. We put it between a hot plate and a cold plate, and what we do is we heat up that hot plate until we get our hot and our cold plate kind of get into an equilibrium range. For example, you might have seen 75-degree mean for a residential insulation. What you're trying to do is determine what that heat flow is through there. So we know how much electricity we're putting in, which we convert to heat so that it flows into that. And then we're just waiting for it to come in equilibrium. We take a measure, we see how much energy we put in, we know what our thickness is, we know what these other conditions are, we apply some math to it, and we come up with a K value. And a K value is reported in BTUs per hour per square foot per Fahrenheit degree or watts per meter Kelvin. And again, we're going to use that information later. Another thing to point out is if you're testing a pipe configuration, you look down below on the lower right-hand corner of the slide, and essentially we have a similar device, except we're actually testing the pipe. The slight difference is we heat the pipe up to some temperature, and if it's industrial insulation, it's going to be 1200 degrees Fahrenheit. And then your cold side is going to be whatever that ambient condition is, which is usually going to be the room temperature. So from that, you'll also get a K value, which generally is going to be about 15 to 20% higher than it is for the flat configuration. Now, the interesting thing about mineral wool is there's not much of a difference between a flat or a pipe configuration. If you look at other maybe more rigid mineral-based insulations or some of the thin blankets, you'll see dramatic differences between what their flat tests are versus their round tests. Mineral seems to be not as sensitive to that. Anyway, we'll take that information and we'll use some software. And those of you out there might have used a program called 3E+. We'll talk about going to specifics of that a little bit later, but essentially we'll take some assumptions like we have in the upper left-hand corner of this slide, and we put this into 3E+, and we do some calculations. So going over to the right-hand side and looking at the top table, we have a configuration where we use shiny jacketing, and the table below uses what we call dull jacketing. So this might be canvas or some other kind of dull, non-reflective surface, where shiny might be stucco embossed aluminum or stainless. So we look at the bare pipe surface temperature on the top table. You'll see we have just a little below 1200 degrees Fahrenheit. So you have a little bit of heat loss through that wall, but metal conducts heat quite readily. Your heat losses are on the order of 26,000 BTUs per hour per foot length of pipe. And remember, this is an 8-inch pipe. One thing to notice here If I just put on a 1/2 inch of insulation, and just to be clear, nobody makes, most industrial insulations aren't a 1/2 inch thick, and certainly not mineral wool, calcium silicate, or perlite. What happens is, even though we put this increment on, we would think that our surface temperature would it drops quite a bit on that first increment. So we went from almost 1200 degrees, almost down to a little below 700 degrees, so almost in half. But you see, as we kind of increment it up, we're not making as big a drops with subsequent increases in thickness. And that has to do with the geometry of the pipe. If you imagine you have this pie wedge of insulation over the top of this one section, you have a lot more insulation over that little wedge. So you have a lot bigger temperature drop over that first increment than you do on the subsequent drops. The other thing to notice here too is even just that first increment of insulation, you're reducing your heat loss by a factor of 9, almost 10. You're going from 26,000 all the way down to 3,000 just with a 1/2 inch. But you see, as we keep adding, we don't see as much of a jump. The other thing to note here too is we always try and shoot for a surface temperature of 140 degrees. The reason for that is that when you touch something that's 140 degrees, it takes several seconds to get a 3rd degree burn. So if you have that surface temperature 140 degrees or below, you can at least touch something, realize it's hot, and move your body part away from it before you get burned. So that's critical. But note here that if I'm using stucco embossed aluminum or stainless steel jacketing, I need 7 inches to get down to 140 degrees Fahrenheit. Whereas if you look at the table below, I only need 4 inches to get to that. That's because that metal jacketing holds in heat. It doesn't dissipate it as efficiently, even though if you look at the heat loss, it's going to be the same for 7 inches, but the surface temperature is dramatically different. Something to keep in mind when you're doing these calculations, and you'll see that emissivity in the software, and that's what that stands for, and it'll have a description next to it. But anyway, your heat loss in general at a given thickness is going to be similar. So kind of moving on with that, we'll move on to fire. A couple of things that we need to know, and I think it goes without saying that we don't want to fire in a facility where we're processing chemicals. Generally, there's a huge downside to this. Of course, there's the safety aspect of this, and even assuming that nobody is there and nobody's there to be hurt in the event of an issue, you still have loss of assets, loss of product, and there's a cost of downtime, which can be substantial. So we want to be mindful of that. We want to know how an installation is going to behave in that kind of environment. So what we need to know is a couple of things that we're looking at. One is flame spread, and those that have been in the industry a while know what this is, and we'll talk about that a little bit more in detail. But really what we want to know is, if I put a flame source next to something, is this flame going to start propagating on, or is it going to self-extinguish or just stop right where the flame source is? There's also the issue of combustibility. Is my insulation going to be a potential fuel source? There are some that are used, in other applications, not industrial, but maybe more residential, that might be that might give off, they do have some embodied energy that does cause them to flame or become a fuel source. There's exotherming. Now, does our insulation heat up faster than the system when we start it up for the first time? That could be a potential problem for us, so we need to know how that's going to work. And finally, we want to know what the behavior of our insulation is going to be at high temperatures. We want to make sure that it's going to remain intact and do what it's supposed to do. We want to make sure that it doesn't warp, doesn't crack, doesn't delaminate, char, settle, or sink, or settle, or do anything else there. We want to make sure that what we install is more or less what we're going to have at operating temperatures. So start off with anybody that's ever seen one of these tunnels. This is a very simplified view, but essentially we're running air through this tunnel. We're going to install a sample on the underside of this lid that's at the top. We're going to put a sample there. We're running air through there at about 240 feet per minute. And there's a flame that's impinging on the edge of that sample. So as the air is going through there, the thought is that you're going to draw that flame across the surface of the insulation or whatever material that you're testing. So as you're doing this, you also want to measure how much smoke is coming off of that product. And quite honestly, this is what usually kills people is smoke inhalation. It's usually not the fire itself. And how that works, it's just a light sensor that you have a light that shines through the duct, and as smoke passes over, it's analogous to a cloud passing through the sky. So it's going to occlude part of that light. And so from that, we get data, and we apply some math to it, and we come up with some numbers. So generally speaking, this test is going to run for 10 minutes. And for a flame spread of 25, that flame is going to propagate just a little under 5 feet, about 4.8 feet or so. Doesn't mean it goes, just 2 feet or whatever, but that's usually the maximum that you want for an exposed application is 25 or less, and a smoke development of 50 or less. So that's kind of in a nutshell what that test looks like. Another one that we're looking at is combustibility. And combustibility, we just want to know what happens when we apply heat to our product. What is it going to do? And the heat of this, what we're subjecting this to is a furnace that's 750 degrees Celsius, or almost 1400 degrees Fahrenheit. We're putting this sample in, and it's a small cube. It's 1.5 inches by 1.5 inches by 2 inches thick. And we're putting in that furnace for 10 minutes. We're looking for a few things. We're looking for the increase in temperature, and a lot of this often happens, but is it a dramatic rise in temperature? Is it a small rise? And there's limits to that in the test method. Does it change in mass, and if so, how much? If we lose all or most of our insulation while we put it in this furnace, it's not going to do us a lot of good in an extreme environment. Or what if it flames for more than 30 seconds? It could almost be considered a fuel source at that point. Those are the things that we want to know. This is one of the few, this is a fire test where it's a pass-fail. Usually a test is usually just a test until you apply some criteria to it as to whether it's a good or bad result. But in this case, if you exceed that temperature, the maximum exotherm temperature, or you lose too much mass or too much flaming, you just fail the test. And then another one that's pretty common, particularly with high temperature insulation, is we want to know what's going to happen to this material when we subject it to high temperatures for a longer period of time. ASTM C411 and C447, they help establish the maximum use temperature. And again, we want to make sure that it's going to remain intact and not do anything weird at high temperatures. So what we're looking for there is we'll take the insulation and actually install it on a pipe, and that's the top section you see here. We'll have a 1200 degree pipe. We'll install the insulation on that pipe while the pipe is still hot. And what we're looking for is exothermic. We don't want that pipe to rise in temperature more than 200 degrees higher than the pipe temperature. Also, we want to make sure that we don't see that insulation sag more than 5% max on the top as it goes through that 96-hour test condition. So if we can pass that, then the material passes, or you can say that you can use it for applications up to 1200 degrees Fahrenheit. Now, maybe in some situations you might do another material type. If it sags too much, or you have too much exothermic, then maybe you need to lower your maximum use temperature for the product. But this is common for our mineral wool products. The bottom one is when you test it in a flat orientation. It's very similar to the one that you see on the top that we use with a pipe, except we're just putting the material over the top of that bottom over that heated surface, and then we turn it on. And we're looking for the same thing. We're looking for delamination, warpage, shrinkage, any kind of deformities that are going to compromise the performance of the system when it's installed. At this point, we're about halfway through our presentation. Are there any questions that we have from the audience?
We don't have any questions so far. So I think you can probably proceed. I'll just remind everybody that if you do have questions, to use the questions tab on the GoToWebinar panel, and then submit your questions that way. So we'll circle back and see if we have any questions at the end.
Okay, very good. Thank you, Jared. All right, folks, moving on, we're going to talk about corrosion under insulation, or CUI. A very common problem in industrial applications. Basically what happens is we have an insulation system like we see in the upper left-hand corner of the slide. But if we add just a little bit of water and some chlorides, and usually the chlorides are, there's going to be some present in the insulation. There's no such thing as chloride free. and sometimes you're going to have some water that comes in. Generally, it's going to have some chlorides in it, and so that's going to come into contact with when that comes into contact between your steel pipe and your insulation. It's if that water is allowed to stay there, then you start creating this chemical reaction, because those chlorides act as a corrosive agent. That water is a carrier that connects that together and helps that reaction to happen. If you take away the chlorides or the water, then we don't have that corrosion. But if those are present, that happens. I always think it's analogous to the picture right below it, where you have a light bulb that's connected to a battery, and you always have a chemical potential, much like a battery. And as long as you don't have that flow of electrons, everything sits there and it's unreactive and nothing happens. But as soon as you add the water and chlorides and can connect everything, that's when you start to have that reaction, what we call corrosion. I think we generally know it as rust, but it can take several different forms. But rust is what we're most familiar with. In order to have the corrosion, we need to have heat, because below a certain point, that corrosion rate just slows down dramatically. Corrosive element, which is generally chlorides. There's other things that are out there as well. And then water, that acts as a connection and transfer, helps to transfer those corrosive elements to the metal surface. Looking at temperature ranges, if it's below freezing, ice is not a good conductor of electron flow. And if you're at cryogenic temperatures, then usually oxygen is going to be in the form of a liquid, so there's just really nothing there to cause that reaction. As soon as we warm up to 32 to 300 degrees, this is kind of where everything happens. You have oxygen, because that's just the world that we live in. There's water if it's available, and if there's heat there, that helps to drive that reaction, because heat helps to increase the rate that chemical reactions happen. The optimal temperature is going to be between 200 and 240 degrees, where you're right at boiling or maybe slightly above. So if you have a wet insulation on there and you're trying to dry that off, you're going to have a much faster reaction there than you would be if it was hotter or colder. And at temperatures above 300 degrees, water just isn't available. So unless you have some other corrosive element there, generally you're going to be limited. So the question I used to ask myself is, if why is COI a problem if we're looking at ranges at say 600 degrees and above, and industrial applications are going to be in the 1,000 to 1,200 degree range? Why are we even worried about COI? Well, the problem is that piping for these industrial applications is plain carbon steel, which isn't as resistant to corrosion as other metals like copper. Copper will form an oxide layer, which helps to protect it and reduces the rate that things corrode, but not so for steel. A lot of industrial processes aren't continuous. We turn them off, everything cools down a lot of times over the winter time, and over a period of time, moisture collects in the system, and then we go to turn it back on again. We have water that's entrained in the system. The other part of this is industrial installations as a category are going to have higher densities and greater thicknesses, and they can hold more water than lower temperature application or insulation. In some cases, industrial insulation can hold up to 3 to 4 times its material weight. So if I'm looking at something like a fiberglass product that might have a 4 pound per cubic foot density, and versus 8 pound for mineral wool, or 15 pounds for something like a perlite or a calcium silicate, there's just a lot more material and stuff there to hold water. So that also creates a problem. It takes a lot more energy to heat up and evaporate that water. So it does stay around for a longer period of time, and hence the reason we have more corrosion. Some of the strategies that they use to prevent corrosion under insulation that we see as water repellency. So that's if we make a water repellent insulation, the water will shed away from the product and not even get to the piping. We know that we have to deal with reality, and that means that we have to make sure that we seal everything well, and that our insulation is butted tightly together. Might not always be the case, but it's certainly a good place to start. And again, the Owens Corning Pro Section WR products do feature water repellency to address this issue. Another thing that you can use is corrosion inhibitors, and that's where you put a corrosion inhibitor that's kind of entrained into the product. that's not a bad idea. It helps to neutralize corrosion. Maybe the only problem is that if it's in the insulation and you're using a corrosion inhibitor, it works really well at that point of contact between the insulation and the pipe itself. But on the sides and possibly the bottom of that insulation where you might have a gap, you have a hot, humid area where you could potentially have corrosion. If in cases where you have flooding and things like that, that could be an issue, but it's something to think about. And then finally, we have kind of the belt and suspenders approach, where you would have water repellency coupled with corrosion inhibitors, so that you're repelling water, and any potential water that does get in, you have a corrosion inhibitor to deal with it. So you have kind of the best of both worlds there. Unfortunately, it doesn't always work out that way. A lot of water repellency things, treatments will burn off at 600 degrees Fahrenheit or so. So any material that sees that, usually close to the pipe, is going to be burned off and actually can become more water absorbent and pearl-like, and that can happen with it actually will absorb the water. So it's fundamentally what the real solution is you want to have proper installation. You need to keep the water out to begin with, but again, it's always that question of you want to keep the water out, but what do you do if it gets in? Well, you want to make sure that that you're jacketing properly, overlapping your joints and caulking them where you can. You want to make sure that you shingle your joints, just like you see over here on the right-hand side of the slide. You want that water to hit and then shed off rather than go into the seam. A lot of times, I have seen images where you'll have the seam right along the top of the jacketing. I live in Colorado, and so if there's snow will sit there on top of that, and water will actually through that capillary effect work its way through the jacketing. So you always want to make sure that you're shingling that. Another possibility are drainage holes. And I know we said, don't put any penetrations in it. Now we're saying put holes in it. Well, if the holes are on the bottom, any water that hits on top is going to shed, or maybe if you might get a little bit that comes around, but that water is going to flow out rapidly. And I have seen that in some specifications. Then finally, if you're in a high traffic area, use thicker jacketing. A lot of times we'll use a thin jacketing on high traffic areas where people are climbing over the piping, and that's where it gets kinked or damaged or penetrated or cut or some other way that you're going to introduce water into that system. So the best way is really just to keep the water out to begin with and make sure you're detailing things well. Okay, next we're going to talk about pipe acoustics. This is our final segment here, so we're on the final leg, guys. Just to start off with, and again, I know a lot of you are familiar with this, but just to kind of, just as kind of an overview, we look at acoustics, we pretty much understand things are loud. We're down in Houston, so the Astros are doing well, so we hear a lot of noise. So we understand what that sounds like, but we also know what quiet is and what it should be. And so we have a good sense of that. Maybe we're a little less clear on is we have sound spectrums that we have over here in the lower left-hand corner, and those are kind of the quality of sound. So we might have a low rumble where we actually feel that vibration physically, or we might have a screech. So anybody that's ever taken their kids to McDonald's in the ballroom and heard them scream knows what I'm talking about. So we want to be able to address different types of sounds. Usually in industrial applications, we're going to have something that's more leaning towards the lower end of the spectrum, say between 100 to 1,000, as we see here in this example. And then finally, just to kind of give some context as far as when we say louder or quieter than, when you hear something that's perceptibly louder, it's going to be plus or minus 5 decibels. Perceptibly louder is going to be plus or minus 3. Just plain louder or quieter is going to be 5. And things are like twice as loud, half as loud, those are around 10 decibels. So it's not quite this straight line. And in fact, they use logarithms in this. So there's a lot of a pretty wide spectrum there that we're trying to represent in some small numbers. So one of the challenges with trying to make things quieter, it's what do we use? I mean, we fundamentally, the reason we want something quieter to begin with is that in a facility, we want to make sure that the surrounding ambient environment is at 85 decibels or lower. And the reason for that is if we go above 85 decibels, then we need to have hearing protection if people are going to be working in that space. A lot easier to go ahead and insulate that equipment than it, and have a quieter environment than it is to try and make sure that everybody's wearing their hearing equipment the way they're supposed to. But the question becomes, how do I make things quieter? I need some data. Testing is expensive. A lot of pipe acoustics information is it's cryptic and maybe not as easily understood as we'd like it to be. But the thing I like about ISO 15665, and you see this more and more, it narrows everything down into basically 3 pipe sizes, 2 insulation thicknesses, and 4 weights of jacketing and lagging. So we have performance levels. We have 3 different performance levels that we have to configure with different size pipes. And we'll see this over here on the upper right-hand side. It tells us what basically what configuration we need if we want to have a certain class. Maybe it's A, B, C, or D. So the next question is, well, that's great. So how well do those perform? If we go down to the table below, if you look under A, let's say B2. And again, you'll see some negative numbers there, and that's just kind of an artifact of like just some mathematic things. Those don't represent a physical reality, but it's just really more to make things continuous in that realm. But if you look at a lot of the values at 500 hertz and above, you see as we go from A to B to C that we see pretty significant increases in performance. So remember, we said that 10 decibels is considered to be considerably quieter. So even just adding 4 inches of insulation, and then along with a heavier jacketing, we can make a considerable change in our environment. And to kind of put this into practice here, first of all, we would take that information that we saw in the previous table, and we'd identify the type of noise that we want to use, and maybe it's and let's say it's fans and pumps. We know our noise is generated in a certain frequency range. We know we're going to use a certain size pipe. And so in order to get the most noise reduction, we want to use a class 2, and class 2 means, or class 2C, which means C is the highest level performance. 2 means our pipe diameter is going to be between 12 inches and 26 inches. So if we do that configuration that we see down below, we have 4 inches of insulation, and we're going to be doing, looks like we're going to be to the 10 kilogram per square meter cladding. That will give us the performance of a 4 decibel reduction at 250 hertz, 14 decibels at 500, 24 at 1,000, and so on. So it's a significant reduction. Usually an acoustic engineer will take this information and they'll actually kind of combine all that to get one number, and they'll call it, it's an A-weighted, or something that represents more of the spectrum of what our ear actually hears. But just kind of at a very simplistic, it's kind of an adding and subtracting thing. So pipe acoustics, here's all you need to know. We're just trying to keep our noise level below 85 decibels. That's because of the hearing protection issues we talked about earlier. Owens Corning does have tested systems that do meet the ISO 15665 acoustics requirement. We have a technical bulletin that's going to be coming out here soon, within the next week, so that'll be on our website for your review. Also, there is an additional D category that's been recently added. And so if you look at the plot in the upper left-hand corner or upper right-hand corner, A would be that bottom section there. So if you look at the frequencies and you look at the decibel reduction, so as you go higher in frequencies, it's easier to block that sound. We didn't talk about that earlier, but the analogy, I think, is if you're sitting at a stoplight and you hear somebody in the car next to you playing the music very loud, you roll out the window, it filters out all that high screechy stuff, but you still feel that bass or that kind of vibration that comes through, and that's the low frequency noise. So the high frequency is easy to get rid of, the low frequency not so much. But you can see how those levels increase, and by the time you get to D, you see there's a pretty substantial bump. We're up to around 40, 45, and that's on par with something kind of similar to like a very good commercial wall between offices. So that will block a lot of sound. But again, hard to deal with on those lower frequencies, so we just have to keep adding thickness and mass to deal with that. But the headline there is that Owens Corning has a solution for that. So that's kind of wrapping it all up. We've covered these 6 topics. I've gone quite quickly, and you know, my apologies for that, but wanted to keep things going and make sure that we made sure this was valuable for you and what you're doing. So with that, I turn it over. I'm sorry, just one more shameless plug here for 2 organizations. One is NIA, the National Insulation Association. They have a lot of great information on their website. A lot of this was generated from this. They do have they have appraiser programs. They have calculators that are online. So if you need, it's not even something you have to download, but they have them for condensation control, temperature drops, personal protection, all kinds of things. The insulation material specification chart, I highly recommend. It comes with a lot of information regarding ASTM test methods, what's included with them, how they perform, and they're side by side so you can compare them with different materials. And of course the spec guide, which is a compilation of everything kind of above and beyond that includes not only ASTM but also federal and military specs. You can go to their website there at insulation.org. The other thing that I think is tremendous value is the NEMA 3E Plus software. It's free. And it's pretty easy to use. It's been around for a while, and it's based on ASTM C680. So this isn't something that was just developed by NEMA specifically. They created the program, but the actual calculation methods came from an ASTM method. Again, free software, it works really well. And I think it's used by over 14,000 users. I would also highly recommend the Owens Corning branded version of this, which includes not only what's in the NEMA version, but also comes pre-populated with Owens Corning products as well. So you don't have to input that manually. I guess I'm looking at Jared. We'll open it up for questions if there are any.
First, we have from David. As you mentioned, the C411 test, and then is a 96-hour test. What are the long-term effects of high temperatures and vibration on mineral wool insulation?
Okay, so the question for people who didn't hear it, the question is, what are the long-term effects on vibration on mineral wool? It depends on the application if it's applied correctly, and I guess it depends on the amount of vibration. In some extreme cases, some of the binder can burn off, and it typically does burn off on that first initial layer around the pipe. And if it's subjected to significant vibration, it can settle a little bit. C411 doesn't capture that. They're just looking at it from a temperature perspective. So again, that has been known to happen. I don't know how common it is, but it has been known to happen. If you do have like a high vibration in pipe, it's always a good idea to either secure that somehow using possibly a high compressive strength insulation pipe support, or just get rid of the vibration. They do make couplers to help decouple those pipes and make sure that those incidents don't occur. Thank you, David.
Great, thanks. And I have a couple more questions for you, and then I do want to mention that we also have Jeff Deneen on as a panelist. He's one of PI's reps in the Great Lakes Midwest region, so he'll be able to answer some questions too, maybe if there's something more on the sales side. But another question, do you have any acoustic data on hybrid systems using mineral wool and mass-loaded vinyl sheeting?
Yes, the ones that we have, both C and D, those do have mass-loaded vinyl. We have the C, I believe, has a mass-loaded vinyl underneath the jacketing. D has mass-loaded vinyl between the layers of mineral wool and on the outer section. We also have data for foam glass used with mineral wool. We're still developing that bulletin, but we do have data for that as well that does satisfy that shell D specification. So we do have a hybrid test method for, or hybrid results for that.
All right, we have another question from Lori. How many thicknesses do you offer? And I'm assuming she's referring to mineral wool.
Let's see the pipe sections. I'm not sure. I know that we have the standard ones, I believe, 2 and 3 inches, and we do have nested configuration. Boards, we I believe we started at 1.5 inches. I think all products we have 1.5 inches, 1 inch in some densities, and I think up to 4 for most products. And I think we can go thicker on some specialty ones. I think as thick as 6. Might need to contact one of our sales folks for those specifics. Yeah, they're available. A lot of their competitive dimensions with other products that are out there.
Yeah, and also on that, I would just say contact your DI rep, and they can certainly communicate with Owens Corning and get all that information for you. That's all the questions we have that have been submitted. I'll give it a couple more minutes. And while I'm giving it some time, I do want to just kind of announce next week's webinar. We already have scheduled. Visit the distributioninternational.com website under our resource center. You can see the information on that. We have our manufacturing partner ITW presenting on commercial building chilled water applications. So we're excited about that one. And then we won't have a webinar the week after that because the NIA Fall Summit is that week, but we will pick them back up the week after that on the 13th. So we don't have any more questions, so I guess we'll get down to the door prize. So I'm going to ask Doug to pick a number between 1 and 31.
1 and 31. My apologies in advance for people that didn't get the right number, but I'm going to go with 17.
All right, that'll be Kip. So Kip, I'll be in contact with you and discuss the logistics, get you your $200 Amazon gift card. We like doing the door prize as a way to say thank you for participating in this initiative and supporting it. It's still kind of new, but it's gaining momentum, and I think it's been going well so far. I want to thank Doug and Owens Corning. I think Jeff as well for participating in this, supporting this initiative. I think there was some great information today, and we'll look forward to doing another one with you guys soon.
Excellent. Thank you, everybody.
Anything else?
No, that's it. Thank you, everybody, for attending. I know it's tough to listen to these after lunch, but I really appreciate you listening in. So thank you, and thank you, DI, for giving us this opportunity. Y'all have a good day.